Can you guys hear me? All right, cool. Hi, I'm Navjot Garg, and was rendering lead on Dragon Age: The Veilguard. Very quickly, Dragon Age: The Veilguard was the latest installment in Dragon Age series, developed on Frostbite engine, and it was launched on PC, PS5, Xbox Series X, and S. We had a small rendering team at BioWare working on the project, around 5 rendering engineers, and we were also supported by Frostbite rendering team. So what's on the agenda today? I'll go over the motivation or goals that we had for our appearance editor, how it worked, appearance editor, how it allowed us to create a variety of characters, and then the character creator in-game itself, what kind of customizations were supported on that. And then I'll go a little bit into strand hair, some of the issues around lighting strand hair that we solved for the game itself, and the appearance system, which was reused for multiple other systems, like infill characters, dynamic shader variation system, gear system, and at last, some of the takeaways from the development process. Okay. These are some of the examples from the editor tool as well as in-game. So for our goals, the first one was to provide artists enough options so that they can create a variety of characters. And the fidelity that was obtained in the editor was also similar to what we get in the game. We used a common rendering subsystem for both editor and in-game character creator. The dev tools were needed before we could do our character creator, so that kind of helped us scope the number of customizations that we could provide to our players. Fast iteration was another one of our goals, and we wanted to push the boundary on how many customizations we can support and allow the player to create their own character. And last, we wanted to do performance estimates for our characters in the editor itself, so that we can get a good idea of how the performance would look like later on. This is a snapshot of our appearance editor in Frostbite engine. So this was an in-house tool that we developed in BioWare. For creating an appearance, we divided it into 2 parts. One was the head preset, and the other one was body preset. An appearance preset is basically a collection of multiple slots which were authored by artists, and each slot could have one appearance item. An appearance item is basically a container for mesh and material information. The other panel that you saw on the previous slides was the customizer sets that allowed us to do assignment for the appearance items to those slots, choose any kind of hair color or modify any kind of shader parameters, apply any kind of texture sets for makeup, complexion sets, tattoos, etc. It also allowed us to pick the lineage of the character and test that, different gender builds, head blends, skin tones, etc. This is one of the examples. Basically, in this particular example, we are applying a complexion set from a texture set that was created by artists. And then on top of that, we can do additional shader parameters that allowed us to set a specific skin tone value. Another example showing how we did our morphs. For example, in this case, different sliders for adjusting different parts of the nose, including bridge, tip, nostrils, etc. So everything was mapped from -1 to 1 value here. So next, we'll see like how we loaded all our characters from the editor and then into the game. So this was kind of the setup for how we defined our character template. The character template basically included a framework for how the character should look and behave. For the appearance part, like I said, we had appearance preset that we set using the editor that I just showed. And then it contains slots and appearance items being the same as the mesh and material variations. We also had the customized sets like I showed, but that was only on the editor side. For the in-game sites, we had a different front end. We used a common subsystem for rendering our characters. This was called appearance system. What that would do is it would parse the template asset, and out of those, it would collect all the appearance item information. And in the asset pipeline stage, it will do a pipeline cook, generate asset bundles. These asset bundles at runtime are again picked up after parsing the template asset by the game. And there was an appearance component that instantiated corresponding items for those. And once the items were instantiated, we were able to apply shader parameter blocks, which allowed us to do customizations related to the shaders. This appearance system was used for for all of our character rendering in the game. So some of the examples: character creator, which was used for main players customization; infill characters, which was used for seed-based customization for the crowd characters; dynamic shader variation system, which was used for damage over time, combat effects like that; and gear system, which was tied into the inventory and allowed us customizable outfits; and other NPCs, which were not customizable in the game, but they were preset, pre-authored by artists, and they could be directly put in the game. We had 3 different types of NPCs: full NPCs, light NPCs, and swarm NPCs. The difference between these was varied amount of support for appearance customization. Full NPCs had full support, and it reduced as we went to light NPCs, and swarm NPCs had very limited variation. Now we'll go over the character creator that was in-game. So for the architecture, basically, once the player sends the customization data from the UI interaction to customization manager, the data was converted into smaller building blocks, and these were applied via appearance system onto a preview character. Once the customization was finalized, all this customization data was written into persistence, and that was used later on when loaded into the main game or any saved game session afterwards. So customizations were divided into following categories: shader parameters, more features, head blends, texture sets, appearance items, and animation game states. We'll go over these one by one. So this is the example of how we were changing parameters on the shaders and their values. For example, skin tone, hair color, eye color, etc. So the input for this was the shader parameter name and its corresponding value. The way it was set up, we were able to use the unique shader parameter name for multiple shaders that were applied to the character, and therefore change all of those in one go. This allowed us to, for example, match the face and body skin tone with the same parameter name. The shader parameter blocks were used to apply all these customization. Shader parameter blocks are just a collection of the shader names and their corresponding value again. And they are stackable, and therefore we can apply and remove these blocks as required. Next is more features, and these were used to change facial features and body builds. The input for these was the feature ID and the corresponding weight. The weight was mapped from -1 to 1 value. It's very similar to how we did this in editor, but here we had like a custom UI for it. And the weight was mapped basically to joints and how much desired range was required. So accordingly, the transforms would change. We also supported 3 head blends per head. This was done using mesh compute, and like each head blend, each race, had multiple head blends which were authored by artists. The input for this was the 3 head blend assets as well as their weight correspondingly corresponding to whatever desired range we wanted. The one issue we had with this while working on the character creator was the memory consumption. It was pretty high because we were having to store multiple heads for a single character. So the solution for this was we unloaded all the unused asset bundles and reused the asset bundles that were common amongst all the characters. Texture sets were used for doing complexion sets, makeups, tattoos, body or face paints, scars, etc. So these usually were a collection of texture assets that were applied on top of the current character shaders. And this is very similar to the shader parameters, except the textures are asset bundles. And therefore, we had the same issue here where the consumption was pretty high. And if it reached a certain limit, we ran into risk of streaming lower resolution textures. For resolving this, we kept an eye on how we were doing loads and unloads on our asset bundles. Again, not doing any kind of duplication and using only the ones that we needed. We also did a soft references for the assets, specifically for character creator. The reason we did this was because we didn't want to load all the texture asset bundles into the memory at once. So we created soft refs to that. We also created texture IDs, which were a combination of texture path and name hash. Corresponding to the texture IDs, we created these texture asset bundles. And at runtime, using these texture IDs, we were able to on-demand load these textures. The textures once loaded, the texture bundles once loaded, were able to apply these texture assets via shader parameter blocks again. Appearance items. Appearance items are like all the assets like hair, eyebrows, eyelashes, horns for canary, and gear are all appearance items. The appearance items automatically loaded all the customization or variation that was set up in the data by the artist. And then we can do even more customization on top of it by using the previously mentioned shader parameters. Item bundles also had to be loaded and unloaded carefully for each category so that we could keep the memory within budget. And the last one is animation game states. This is very much like feature morphs, but for the body. So this allowed us to interpolate our rig transforms from a male to female base or between different lineages. So we could use the same model and interpolate their game states so that we can get different lineages. We had 4 different lineages in the game, and each had its own height and build, etc. So we could control all of that using animation game states. So some pros and cons for using these animation game states. It allowed us easy control that was exposed to both artist and player. And the transition between lineages and build was easy with this particular customization. We also used same outfits for different lineages, so we could reuse like all the assets. We didn't have to create 4 different assets for 4 different lineages. The same asset worked on everything. Same animation sets also could be worked for all lineages. And the one optimization that we did here was the rig transforms that were applied were only applied once when we were doing customizations. So for example, in editor, we would do it every frame, but in the game, it was only done once the customization was done. And after that, it did not run. There were certain drawbacks of using these. First of all, it took a lot of time for us to set those up correctly on TechNM side. There was a lot of rig-related issues that we faced. Animation itself was done on a base human model. So for other lineages, there were some extreme cases where a hand would clip inside the body or something like that. So those were kind of the issues that were faced by TechAnim. So we had to constrain the value of how much the range was, and therefore that's how we solved this issue. Another issue that we faced was non-uniform scaling, which broke our cloth retargeting. So we had to take a ratio of the base height and the desired height of the desired lineage in order to do a non-uniform scaling, and also provide cloth retargeting support for it. Stand here, one of the most impressive features in Dragon Age, the Veilguard. There's a lot of effort and very complex hairstyles. We supported a lot of hairstyles that are considered very difficult to do in graphics. So we worked very extensively with the Frostbite engineers on this. Optimizations and for performance and memory usage were also done with the help of engineers from Frostbite and our performance team at BioWare itself. We garnered a lot of praise for this particular feature in gaming and tech community. But there were several issues that we had to resolve before we could get it to a workable, shippable state. Some of these problems are now resolved in the latest version because this is already, the game is already 1 year old, and therefore some of these issues have already been addressed in the current version. I'm sure Frostbite Rendering will do like a full in-depth stand here talk at some point. But for now, I'll just talk about the problems that we faced in our version of the stand here. First one, we had a variety of visual environments, and the lighting on the hair needed to look correct in all of those visual environments. We also had an issue with the lighter hair color tones not performing well, or not. It was prone to unexpected changes. So for example, when the character was going from a very bright area to a very dark area, the lighter hair tone would not give us the correct color. And then the lighting model itself did not have any diffuse component, and it was purely treated as specular. So that had certain issues with how the lighting was done. So solution for this, we use fake character lights, and we always had one shadow casting light that had to be present in the scene so that we could get proper shadows. And then LRV and sky sampling was a must for getting correct color for the hair. Another big issue was how the blending for the hair was done with transparent VFX and participating media. For this, we divided our stand hair rendering into two parts, the opaque portion and the transparent portion. So this was very similar to how transparent edge is done, but we added a little bit spin on that. So we added a alpha cutoff that would determine if the hair pixel was above the cutoff, then it was opaque, and if it was below the cutoff, then it was rendered as transparent. We also did a transparent depth pass first that kind of provided a spatial barrier between the transparent portions and other transparent objects in the scene. Basically, we rendered the opaque portion of the hair first, followed by a transparent depth sampling that told us whether the shading point was under or on top of the stand hair. If it was under the stand hair, then we rendered it. Otherwise, we didn't. If it was on top, then we did nothing. And then after that, the transparent portion of the hair is rendered, and followed by the transparent object rendering itself. So that gave us a nice layering of stand hair with the transparent VFX. So as you can see, this is an example of before and after applying the transparent portion of the hair to the character. Another issue that we faced was how the shadows were not good enough for certain scenes, especially the cinematics. So what we did for each stand hair, we rendered special shadow maps that were created using a tight-fitting light frustum, and it was adjusted based on each hair's bounding box. So that gave us very high-quality, high-resolution shadow maps for these strand hair objects. So at any given point, we rendered the shading point for the shadow into either regular shadow map or the strand hair hero shadows. So since it was not in both of those places, we were able to optimize this a little bit by checking the regular shadow maps first. And if there was no hit, then only we will sample the strand hair hero shadows. So you can see in the image on the left-hand side and right-hand side, they have a little bit of difference in how the volume is for the hair is looking on the character. So this was kind of a good visual gain for us. Next is collider sets. So these were used for preventing the hair from clipping inside the character outfits. Basically, the character outfits were the same amongst all the different lineages. Therefore, the collider sets also had to follow the same customization. So we allowed the colliders to be moved based on the skeletal joint transforms, and therefore we could use the same collider sets for any lineage that we had. Talking about the performance a little bit, we had a 6.5 ms budget for 33.3 millisecond frame time and a 3 millisecond budget for 16.6 millisecond frame time. We also had a 2 millisecond time on GPU compute. So this allowed us to render 8 strand hairs in the scene at once. And we had to do a couple of optimizations and put in some constraints in place to meet our rendering budget. The first one is we only did it for PC high and ultra settings and PS5 and Xbox Series X. Only the head hair and the beards were using strand hair. Eyelashes and eyebrows were such small assets that they did not benefit from using strand hair, so they were only card hair. Only the named NPCs that were deemed important by the artists for the narrative used strand hair. And we bundled the strand hair and card hair separately, even though they were in the same asset, so that we could save memory issues on consoles which had memory constraints. So for example, Xbox Series S, we only loaded card hair on it. Hair resolution control was used to adjust the hair resolution depending on the upsampler and DRS settings. And we also disabled hair sim when the hair was off screen or away from camera. We used something called sim lords for this. And we also decimated render strands based on camera distance. Okay. Now I'll talk a little bit about infill characters. Infill characters were used to populate the world. They were like the crowd characters, basically. It was a very data-driven way that we were doing this. So we had all the data stored into a data asset on Frostbite. And we had the characters divided into different lineage, gender, ethnicity, priorities. And based on those, at pipeline stage, we would create IDs and asset bundles corresponding to those customizations. And then at runtime, the same were used for rendering the actual characters. This allowed us to reuse the appearance system here again. And most of the customizations that we did were fixed for these, but we had to use a subset of it. So there was an option of doing all these or baking in all these characters before, but that meant that we had to use a lot of disk space for creating all these character asset templates. So instead, we prioritized that and did everything on the fly. We used certain trade-offs for achieving the performance here. For example, we used only 2 head blends instead of 3 in full NPCs. We also stopped blending computations at longer camera distance. Since the camera was pretty far away from the crowd characters, we could get away without using any kind of feature morphs, and we still had like good enough variety on the characters. We only used a card hair. No strand hairs were used for crowd characters. Shader and texture parameters also were a subset of what we were allowing for the main player's customization. We also did a one MIP offset for textures on platforms with memory constraint. One of the examples is again like Xbox Series S. And for geolords, we did not make any separate low poly models because at that camera distance, the first offset was good enough. The first lord was good enough. We divided our infill characters into based on regions in the game, and that allowed us to do a better content management and also loading and unloading of all the character sets in one go. So next one is dynamic shader variation system. We use this for like doing damage over time effects like poison, etc. On the characters and enemies. We built this to use the shader parameter blocks and use the property that they were stackable, and hence we could like apply and remove them as required. This helped us avoid SRV limitations as well as prevented shader permutation bloat. This is how it was set up. Basically, the replacement shaders were used for each of the shader that was for that particular variation, and these could be invoked from the gameplay timeline itself. So I'll just skip over this in the interest of time, and wanted to show the video. So you can see like there are 3 characters here, and that's the burn effect being applied on top of the characters already customized. And last is the gear system. These were basically like the pre-built armor sets that were a collection of appearance items, and they were tied into the inventory itself. And some of the takeaways, so we started the development on the character customization pretty early, and so that allowed us to scope it very well with the dev tools already in place. And we only prioritized the ones which had a good impact on the player experience. And we kept an eye on memory and made adjustments as necessary. Okay, I'd like to thank these people for helping us ship the game, and thank you so much.
Thank you so much for the presentation. That was awesome. I think we have time for one question or so before we set up for the next. Oh, I see one.
Thank you. For the head morphs, for example, just as one of the examples, do you bake out after character creation, for example, do you bake out that morphed character and then don't morph at runtime, for example, or do you keep all the very assets and morph and animate everything like that?
For the head blends, you mean?
Yeah, for example.
Yeah. So for head blends, basically, like we had a collection of 40 pre-created heads, which we were able to interpolate between using mesh compute. So that's how that worked.
Okay. Thank you.
Okay. Thank you so much.
Right.